On May 16, 2025, the James Webb Space Telescope turned its gold-coated mirrors toward a patch of sky in the constellation Sextans and captured a single exposure as part of a deep field program nicknamed Mirage, or Miracle. Hidden inside that image was a faint yellow speck, only a handful of pixels wide, glowing in the telescope's longest infrared channels and invisible in every shorter wavelength. Most automated pipelines would have tossed a signal like that aside as noise, a cosmic ray strike, a processing glitch, nothing worth a second look. But a research group led by Rohan Naidu at MIT's Kavli Institute didn't dismiss it. They marked it, studied it, and eventually pointed a spectrograph at it. What came back was something that, by the old rules, shouldn't have been there at all: a fully formed galaxy. Within weeks of confirming it, the discovery pushed some of the field's most senior astrophysicists to publicly say that their long-standing model of galaxy formation no longer matched what they were seeing. This is the story of that find, why it's bigger than a new distance record, and why a stack of odd, uncomfortable evidence is building up against our picture of the universe's first few 100 million years. Light travels at about 300,000 kilometers per second, the cosmic speed limit. But the universe is so enormous that even at that speed, a photon can spend longer crossing it than Earth has existed. The universe itself is roughly 13.8 billion years old. For its first few 100 million years, there was nothing to observe. No galaxies, no stars, no chemistry. Just a spreading haze of hydrogen and helium so dense that light couldn't move through it freely. The object's name, MOEM-Z14, comes straight from the survey that found it, the Mirage or Miracle program, designed specifically to hunt for rare, unusually bright targets near the limits of what Webb can detect. The name captured the team's own uncertainty. Was this a mirage, noise or contamination that would fall apart on closer inspection, or a genuine miracle, a real galaxy that had somehow come together far faster than expected? In spring 2025, Naidu's team was combing through Webb imaging from a roughly 350 square arc-minute survey of the Cosmos legacy field, specifically searching for faint, overlooked candidates like this. They found one object that showed up clearly in Webb's reddest filters but essentially disappeared at shorter wavelengths, exactly what you'd expect from light so extremely redshifted that its blue end had been stretched away entirely. When the spectrum came in, it revealed a sharp absorption break at the wavelength where early universe hydrogen swallows ultraviolet light, along with faint but statistically solid detections of several rest frame UV emission lines. Together, these locked in a redshift of 14.44, meaning the light had been traveling for roughly 13, 5 of the universe's 13.8 billion year history. That measurement broke the previous distance record. Astronomers were now looking at light emitted just 280 million years after the Big Bang, when the universe had lived through barely 2% of its current age. To put that in perspective, compress the universe's entire history into one calendar year. MOEM-Z14 is small, roughly 241 light years across, give or take a few dozen. For comparison, the Milky Way spans about 100,000 light years. Standard formation models predict that galaxies at this stage of cosmic history should be dim, disorganized, and slow to come together. MOEM-Z14 instead looks compact, energetic, and strangely mature, as if it skipped several expected steps in a galactic development. So what's powering it? Researchers have floated a few competing ideas, and each one carries uncomfortable implications. Unusually efficient star formation gas collapsing into stars far faster and with far less waste than we see in galaxies today. Extremely massive, blisteringly hot first-generation stars. A small number of them could outshine an entire modern galaxy. An early black hole already feeding on surrounding material and radiating enormous energy as it grows. None of these explanations are mutually exclusive, and any of them would force a real rethink of how the early universe assembled itself. It's entirely possible MOEM-Z14 is a combination of all three efficient star formation, an unusually massive first stellar generation, and a hungry black hole core all stacking together to produce something. This compact and this bright, sorting out which mechanism matters most, will likely take a fresh round of observations, pushing Webb close to its operational limits. The brightness isn't even the strangest part. When researchers broke down MOEM-Z14's full spectrum, they found a specific chemical signature in its surrounding gas, a nitrogen to carbon ratio higher than our own sun's, and far higher than current models expect for a galaxy. This young hair is why that matters. The universe started out almost entirely hydrogen and helium with a trace of lithium. Every heavier element, including the carbon in living cells and the nitrogen in DNA, had to be forged inside stars and then scattered back into space when those stars died. Building up that kind of chemical enrichment takes multiple stellar generations, living, dying, and recycling their material. At only 280 million years old, there should barely have been time for one full cycle. let alone enough to produce the imbalance actually measured. There's a second layer to this. That same nitrogen-rich signature has been seen much closer to home inside globular clusters, dense ancient collections of hundreds of thousands of stars that orbit the outskirts of galaxies like our own. These clusters have long been treated as relics from the universe's first few billion years. Seeing the same chemical fingerprint in MOMS 14 suggests that whatever builds structures like globular clusters may have kicked off almost as soon as the primordial fog cleared, not just nudging the timeline earlier, but giving researchers something new, a live currently forming galaxy, to compare directly against the ancient fossils sitting in our own galactic halo. It would be reasonable to assume this is a single strange exception. Rare outliers do happen in science, but it isn't isolated. According to the survey behind this discovery, the number of bright galaxies at this redshift is more than 100 times higher than pre-Webb models predicted, with some estimates putting the real figure closer to 180 times higher. Since Webb became fully operational in 2022, it has delivered variations of the same surprise, repeatedly distant galaxy after distant galaxy, turning out too bright, too developed, and too chemically rich for the era they're being observed in. What started as a handful of rare exceptions increasingly looks like the norm that matters, because the standard model of cosmic structure formation isn't a casual guess. It represents decades of observation, simulation, and testing, and it is held up to an enormous number of challenges. It isn't simply wrong, but it keeps getting surprised in the same direction over and over. And a model that keeps missing consistently in one direction usually has a real gap in it somewhere. Perhaps dark matter played a bigger role in seeding early structure than current models assume. None of this is science failing. It's science doing exactly what it's supposed to do, running into contradictory evidence and refusing to look away from it. Rohan Naidu has publicly called the widening gap between theory and observation both challenging and exciting. Pascal Oesch, an astronomer at the University of Geneva, who helped confirm the find, has stressed why the follow-up spectroscopy was essential. Photometric distance estimates from images alone can be thrown off by dust foreground contamination or statistical noise. Only detailed spectroscopy can lock in a distance this extreme with real confidence. That caution is what separates a peer-reviewed result from a viral, unverified headline. And it's exactly the standard Nidus team applied before publishing in the Open Journal of Astrophysics. This distance record likely won't stand for long. Researchers involved say Webb appears capable of pushing the frontier back even further, potentially reaching redshifts once thought unreachable, closing in on the era of the very first stars. Other extreme candidates are already being confirmed, including one called Parsec 141 at redshift 1353, corresponding to roughly 310 million years after the Big Bang, suggesting MOMS 14 is simply the current leader in an accelerating race. There's a completely different puzzle buried in Webb's deep field data, and researchers are still debating whether it connects to any of this. When a separate group sorted a large sample of spiral galaxies, by which way their arms wind essentially, which direction each one spins, the count came back lopsided. A clear majority spun the same way. In a universe with no built-in preferred direction, that split should land close to 50-50. There's no obvious reason the cosmos should favor one rotational direction over another. The team behind that study raised a genuinely startling possibility, one that sounds more like science fiction than a peer-reviewed paper. What if that imbalance is a leftover trace of the conditions our universe formed inside? What if our entire observable universe is in some real physical sense sitting inside something like a black hole, across a black hole's event horizon, and from the outside, you're gone for good. But what happens on the inside remains genuinely unknown. What if the interior isn't a dead end, but a separate region of space that keeps expanding on its own? Under that interpretation, the Big Bang wasn't necessarily an explosion into empty space. It might be the flip side of a gravitational collapse that happened inside some larger parent universe at the moment. Enough matter fell together and sealed itself behind its own horizon. In fairness, there's a simpler, more grounded explanation too. The spinning imbalance could be a measurement artifact. The Milky Way itself is moving through space, and that motion can subtly brighten objects rotating against our direction of travel, while dimming ones rotating with it. If our estimate of the Milky Way's own motion is even slightly off, that alone could introduce a statistical bias, no cosmic mystery required. The honest takeaway, this isn't proof that we're living inside a black hole, and it isn't nonsense to dismiss. Outright, either astronomers are looking at several separate, seemingly unrelated pieces of evidence, all pointing in the same uncomfortable direction. A galaxy that formed too fast chemical enrichment that arrived too early, and a patch of sky that seems to have a preferred spin direction. Individually, each could be explained away. Together, they start to look like something worth taking seriously. There's also a quieter story here, separate from any black hole cosmology, the sheer engineering achievement it took to capture this light at all. MUMS 14 sits at an apparent magnitude of roughly 20, and Webb can only see infrared light this faint, because its own instruments are kept extremely cold. Any heat radiating from the telescope's own structure would otherwise drown out a signal this faint arriving. After a 13.5 billion year journey, every redshift measurement, every emission line, every chemical signature pulled from MUMS 14 spectrum exists only because that engineering worked exactly as designed. Webb's deployment, unfolding its sunshield and mirror segments over nearly 2 weeks of tense maneuvers after its 2021 launch, involved hundreds of single points of failure, any one of which could have ended the mission before it produced a single image. That a telescope built on such a fragile sequence of events is now routinely rewriting. The timeline of cosmic history is worth sitting with on its own. Roughly 13.5 billion years ago, that faint speck of light left its home galaxy, carrying a question astronomers still can't fully answer. It hands the field a blank page and dares them to fill it in, and Webb won't be working alone much longer. Ground-based observatories under construction, along with future space telescopes built to map dark matter and dark energy across huge swaths of sky, are expected to turn up dozens or hundreds of similarly extreme candidates within the next decade. What currently looks like a small hand-picked set of impossible early galaxies may soon become a large enough population to study statistically, rather than treating each one as an isolated anomaly. That shift from a handful of strange exceptions to a measurable class of objects is usually the moment a field stops patching its old model and starts building a new one. Somewhere beyond what MUMS 14 has already revealed, there are galaxies older, stranger, and harder to explain waiting to be found. The only real question is how much further back the next mirror and the next generation of scientists will be able to see.